Hey, you guys, I just thought I'd make you this quick video. My name's Kristen Rowan. I am your kind of facilitator for the online course. And I know online courses are very, very challenging. And that's because most of it you have to do yourself. You just have to go read the information and see if you can glean enough from those textbooks and those resources to be able to answer questions or things that are being asked of you. And I know that it's very, very difficult. So anyway, I just thought I'd make you a quick video about project number 3. Which kind of brings together a lot of the chemistry you've been learning in these last couple chapters. And that's kind of the reason for it, is to make you think about all that chemistry and try to put it together. So project 3, part 1, the first part was being a scientist. It's always fun to actually do reactions. So the first thing you wanted to do was view the reaction. If you viewed the reaction and kept your notebook, the idea was to be observant. How observant could I be? And how could I use that information later? So that hopefully you'll watch that video, record your procedures as if you were actually doing the experiment. So you should have a nice notebook, which shows the purpose. You can write a purpose for this experiment, basically to learn this information, and then write what reaction you were running or what was being run in the video and so forth. The first page is a scan of your notebooks, but I thought I have a little animation here for you that I thought was kind of fun. Here is the reactant that you're starting with. The reactant that you're starting with is copper 2 chloride dihydrate. And copper 2 chloride dihydrate is this nice blue solid right here. You can see it. Now, then the first thing that's done is it gets dissolved in water. And when it's dissolved in water, it'll just change to this nice blue color. And that blue color is that solid releasing those copper ions into the solution, which now have an aqueous label, and making that blue solution. Then after the aluminum gets added, you see hopefully a reaction will start. It won't start immediately because things have to just take a minute to get going. And once they do, you'll start to see some changes. So in this picture down here that you're seeing, the aluminum has just been added. And before the aluminum starts to react, in that kind of microsecond there, you've got copper 2 ions floating around in the solution. You have aluminum solid in that, so now it's kind of floating on the top. And you have chloride ions floating around in solution. Now, as this sits, it's going to start changing. And there's a couple changes that can be seen here. And one of them is some solid material kind of growing on the outside of the aluminum. And now you might guess, sure enough, that's copper metal. One of those things, the project for this is copper metal is being kind of pulled out of the solution. We dissolved it in, now it's being pulled out on the surface of the aluminum. And then the aluminum is going in. And also some changes you might see here is some kind of condensation on the inside of the flask. And what that means is that something got hot enough, that reaction got hot enough in order to vaporize some of that water, and then it condensed on the inside surfaces. There was also, if you look closely, and I don't know if you can see it in this picture, it doesn't look like it, but there is some gas being formed in here. Now, of course, if there's condensation, that makes you think some water vapor went up into the air and then condensed on the sides of the flask. That's true. There's also some gas being produced that's a flammable gas. So you might think maybe that's hydrogen. And sure enough, it is. If you light it on fire, it pops. All right, what else do we have on here? This is continuing to go. I just wanted to show some pictures of this reaction because sometimes if you see it and then you think about it, it can help you with the project and thinking about what you're supposed to be seeing chemistry-wise. Anyway, so it's continuing on. It looks like a lot of my aluminum in this picture has disappeared, and it looks like I've got some copper metal. And then I just keep on going. Now, this isn't the greatest picture because, a lot of the copper metal that is created kind of sank to the bottom, and you don't really see it in there, but it is in there. Because we saw in the previous slides, if we go back a little bit, you saw that really bright blue, that was the copper before it came out of that solution. And you'll notice a lot of that bright blue is gone. And that's because that copper ion has been being converted into copper metal on the surface of the aluminum, but then it sinks to the bottom. So it's a little hard to see. And then we're continuing on. You'll notice you have some copper ions still in solution. So that means that copper reagent must have been the excess reagent, and the aluminum must have been limiting. Otherwise, you would not have noticed that in this flask. And then our final picture, I let this guy sit for a while and I took the picture. it's not the greatest picture, because what it's not showing is copper metal. It's showing almost what looks like a white solid. So I don't really love this picture, but there is, if I were to jiggle that flask, like this, I mean, I've been playing with this reaction for a long time, and if I were to jiggle it, you might see some of that copper metal kind of floating up into the solution. This one, see, these guys have been sitting for a while, and when they sit for a while, they do some strange things. That's kind of like that with anything, like when you let your cheese mold in the fridge, it's doing some strange things. Chemistry is no different. You get some changes as those chemicals sit in contact with each other. But anyway, here's a picture. So let's move on. What I did want to show you here was a picture of a lab notebook. So your lab notebook, the idea in chemistry is not only to learn how to see into chemical processes like you're learning, but also to take good notes. Good notes is a good skill in any field. All right, so let's go to the next part. Part 2 is thinking like a chemist. So when you think like a chemist, you don't look at the coffee that I'm drinking. You actually look at the coffee that I'm drinking and you say, I wonder what's floating around in there. It is the same with these flasks. When I look at these flasks, I don't think, well, I'm just going to say, oh, it's green. Yes, it is. It is green, but it's also got some dark solid on the bottom. It also has some color in the solution, and it also has some white solid. Like I said, when you let these guys sit, they do crazy things. Thinking like a chemist might be looking at this and going, look, I have a light blue solution. You'll notice in the lower right of your screen, you see a light blue solution. That is where I put the copper 2 chloride dihydrate in there. It dissolved, and then you saw just the blue solution show up. This one, I never put any aluminum in, and that's why you see it look just like this. And it doesn't have any of those weird changes. So in part 2, the idea was to be able to visualize, think like a chemist, be able to visualize dissolving. So I always love the gifts. Gifts help us visualize some things. So what this gift was trying to help us visualize is the dissolving of an ionic solid in water. Water is the red molecules with the positive ends because water has hydrogens on that side. And then it has the oxygen, which has like a kind of a partial negative area, and these guys have positive areas. And water can then pull away cations via its oxygen, or it can pull away anions via its hydrogens. And this gift doesn't do a great job showing that, but that's what this question was supposed to say. Supposed to try to elicit in you this thought of describe in your own words what is happening on the molecular level, like this gift down here, as the copper 2 chloride solid dissolves in the water. Now, I kind of have a mistake there. I would have said copper 2 chloride dihydrate dissolves in the water. And as the water, but then I say it here, from the hydrate dissolves in the water. Is this even possible? So that's just kind of food for thought. It's getting you to think about, what does that actually mean? Because when I have something like a hydrate, which is something like this is a hydrate, which has water molecules attached to it, and it's a solid. Then when I put that in water, these waters are trapped in the solid material. So when I put it in water and dissolve it, what I should have done is made my color, say these waters a different color. No, I'm sorry. I should have made the other waters a different color, like this. And then the waters that I dissolved it in, I should have made black. So then when this dissolves, you'll notice the waters get spit out on the other side. And these waters came from this solid. The rest of the solvent is the other water molecules. And now you can't tell the difference because water is water. It doesn't matter where it came from. So you wouldn't see red waters and black waters. You would just see water. But what does that mean? That does mean that some of the water did come from that solid. And that's what I was trying to get you to think about here. So what does dissolving mean anyway? I have a link for you there in that document. I think it's Tyler DeWitt who does a really great job of describing things, period. I did look at that video recently. I thought it was a really great way to describe dissolving. So anyway, the next thing you're supposed to do is type the balanced chemical equation for the reaction. And I've already given you, you can go look up, it tells you the words there. making a word equation into a chemical equation. It's a way to symbolize what's happening in my flask down here, because that's what we're trying to figure out. All right, so you're supposed to type that chemical equation for the chemical reaction that we're running. An equation is a symbolic representation, sure. The reactants and products are given in a word description, and there they are. All right, so now this letter C here is talking about that dissolved copper 2 chloride dihydrate will impart a light blue color. You see it down here in the lower right to the solution due to the presence of hydrated copper 2 plus. Dissolved aluminum chloride is colorless in aqueous solution. These are clues for you in order to help you kind of understand the process of what's going on in that flask. This knowledge can lead to the discovery of which reactant is the limiting and which is in excess. Now you'll notice in the upper right of your screen, you'll see a solution. This was the final solution of what it looked like after the reaction was finished and all the aluminum was eaten up. So in that example, the aluminum was the limiting and the copper 2 chloride, there must have been some excess, hence the blue color. I have another little GIF here, or not a GIF, but where you just overlay images, and it shows after I dissolve the copper 2 chloride dihydrate, it becomes that nice light blue. Then I put in the aluminum. Then the aluminum is reacting, doing its thing like we saw before. Copper is coming out on the surface of the aluminum. It's continuing to react, but you'll notice that that blue color is disappearing. The blue color is still disappearing, but you might notice a big, huge chunk of aluminum that's left over. So after I let this sit for a good 24 hours and didn't disturb it, I came back and copper had really grown all pretty all around here, but you'll notice you had some leftover aluminum. So in this situation, and notice all the blue is gone. That's because the copper reagent, the copper chloride, copper 2 chloride dihydrate, that one was the limiting and the aluminum was in excess. So that's how you can use these visual cues to know that you had more than one reagent than another. That's what this one's talking about. All right, so now we're into calculations. And calculations sometimes are a little bit more challenging, but if you remember all those conceptual things that I was just talking about, if you can conceptualize how you know that there's something left over or something used up, or which one's limiting and which one's excess as far as the reactants are concerned, then it can help you understand your calculations. So I really want to encourage you to go look at this module 3 exploration number 2, because there is a little, they call them an exploration, where you just kind of click through it, and it talks about these calculations and how to do these calculations for this experiment, for this project. So I ask you to do what? What do I ask you to do here? Pretend you're doing the experiment, access the mass of the copper 2 chloride dihydrate, aluminum, and the volume of water you will use via the quiz. Once you start the quiz and have recorded the amounts in your notebook, perform the calculations and populate the table, this table. Show all your work clearly typed, because remember, in this online class, typed work is checked by Turnitin for plagiarism, and that's why we have to do that. So please make sure, because I have to grade it as such. If you give me pictures of your handwritten calculations, and then I am reviewed later for grading those things, I will get reprimanded for that. You are supposed to have them all typed so they can run through there for Turnitin. Anyway, submit your answer to the quiz to check your work and for verification of by your instructor of the quiz values used. Because if you just give me values down here and then you just start plugging and chugging and doing things, that's not the plan. The plan is to go to the quiz, get the values. On the next slide, I show you what they would look like, and then use those in your calculations. Okay, so what are we going to do with those? Let me just jump over there just to show you. There it is. On this slide, you see this is what you would get out of the quiz. You'd get something like this. You'd get a mass of copper 2 chloride dihydrate. And these quizzes, how they represent values, are in scientific notation. You see them here. This is 2.15 times 10 to the 0 grams. Anything to the 0 power is 1. So this is 2.15 grams of copper 2 chloride dihydrate. This one is, now this is in scientific notation, so it's to the -1. So this is 0.1200 grams of aluminum. And then the next one is 89.0 milliliters of water. So that's what you get from the quiz that you're going to use for your calculations. So let me run back and we'll look at what we were talking about here. So on this part A, B, C, and part 3, A through F, the first part is to determine the theoretical mass of copper produced based on the limiting. Now, of course, you have to know which one is the limiting. So if I remember correctly, 2.15 grams of copper 2 chloride dihydrate, 89.0 mils of water, 0.1200 grams of aluminum. Let me go see if I got that right. 0.12, yes. That was the amounts that were given to me from my quiz. So now I have to look at the mass of this and the mass of this and determine which one is the limiting. Again, I encourage you to go look at that exploration, because that exploration goes through all of these calculations for this reaction to help you with this project. Not to mention it's my favorite reaction. That's why I created the exploration for that. So anyway, I'm not going to go through all those calculations here. I want you to go and look at that module to the exploration and work through it. And then maybe I'll go through one real quick here, but either way, not too much. So on this next slide, that's why I just put this table up again. And I'm like, well, let's look at one. So I love it. Maybe I just like to do these calculations. So 2.15 grams, 89, but I warn you already, I'm writing with my mouse, so it's not very neat. And then we have 0.1200 grams of aluminum, theoretical mass. So if we think about our chemical reaction that we are working with here, it looks like this. So we have this guy plus aluminum to make aluminum chloride. You were given all the products and everything like that, plus copper metal, copper solid. So you want to put in your phase labels, and I'm going to put a 0 there because he is in elemental state. And remember, all elements have an oxidation number of 0 in their elemental state, and that means they have not yet lost or gained electrons. Same thing with the aluminum over here. Here's a solid. This is aqueous. And then we also have our waters that were kicked off. Let me change my color because red is not the most pretty color. And then I'm going to balance this. So to balance it, there's 3 chlorines here. So, and there's 2 chlorines over here. So 2 and 3, least common denominator is 6. So I'm going to put a 3 right here. Then I'm going to have 2 right here. So I have 6 chlorines, or chlorides in this case. And then I would have 3 times 2 is 6 waters. So I'm going to put 6 waters over here. And then I'm going to put 3 coppers. And then I'm going to put, and then I'm done. Oh, wait, no, I'm going to put 2 aluminums right there. All right, so that is my balanced chemical reaction. So now I have 2.15 grams of copper chloride, 0.1200 grams of aluminum. And the idea now is to say, well, how many grams of copper can theoretically be made from both of those amounts of those reactants? Now you notice the water isn't doing much of anything. And what else isn't doing much of anything are these chlorides. These chlorides are called spectator ions. And spectator ions don't really show up. They're there, and they need to be there because where there's a positive, like there's on this copper, there needs to be a negative. Where there's a positive on this aluminum, there needs to be a negative. Okay, so that's why that's why they have to be there. That's just the rules of the universe. But now to figure out this question, which is theoretical mass of copper metal created, I would need to convert grams of this copper chloride dihydrate to moles. Now, this is one method, and I'm just going to do the one method here because there's a couple methods. But if I can go from grams to moles, and then this number of moles of copper chloride dihydrate and then do the calculation and say, well, how many moles of copper will that create theoretically if I had enough aluminum? So when you're doing it this way, you're thinking you have enough of the other one. So alternatively, I can go ahead and say, well, what if I do the same thing with the aluminum? I say this much aluminum, and then I'm going to say I'm going to convert that to moles. And remember, you do that with molecular weight from the periodic table. So the molecular weight of aluminum is 27 grams per mole. Copper chloride dihydrate, I think off the top of my head, is like 170 point something grams per mole. So you take that, convert it into moles, and again, figure out how many moles of copper can be created. This is using the mole ratio for this one and for this one between these two reactants and products. Figure out the number of moles, and then of copper that can be created by the aluminum, of copper that can be created by the copper chloride dihydrate, and whichever one is the smallest, the least amount that is being created is the limiting reactant. So let's say, for example, that my solution remained blue, and I know since it remained blue, my copper chloride dihydrate must have been the excess. And that means that this aluminum here is the limiting. That one should create the smallest number of moles of copper, and that I could then take to grams, and that's the grams that I would report right here. This calculation down here is now no longer needed. I only used it to determine which one was the limiting. So that's a method for determining a limiting and excess reactant. So then the expected solution color over here, we're trying to say, well, if I determine that aluminum is limiting, it's going to be all gone. And what's going to be left is the copper 2 chloride dihydrate, some of it. And then you're going to, I would say it's going to be, right? I would just write here blue. But then you're going to have to explain that later. So I have some pictures over here on your right. The top one is showing if copper 2 chloride dihydrate had been in excess, it would remain blue. And then the bottom one is saying if the aluminum was in excess, there would be no blue and there would be aluminum left. So hopefully that helped. Percent yield is the how much you recover from what you expected. So percent yield is actual divided by theoretical. Actual what? You would say the actual number of grams of copper that was yielded. Now, since you were watching a video and you weren't actually doing this experiment, you guys will do or have done a stoichiometry reaction experiment in your science interactive labs where you mix things together, you make calcium carbonate, you filter it and dry it and all this stuff. Just, it's kind of like that. That's what we're doing here. So I have here determine the mass of the filter paper plus the copper produced, assuming a percent yield of 68%. 68% of what? Of the theoretical. So if you take 68% of that and say, well, that's my percent yield, add it to the mass of the filter paper. Now, where did the mass of the filter paper come from? That came from the video. Anyway, and then you show all your work there. So hopefully that helped with this calculational part of part 3. Now we're not done because we are definitely not done calculating. Because when we're thinking like a chemist, we look at a bucket of something like you have up here in this upper right picture. And we know this color is telling us that there's something dissolved in there, Cu2+. And we already talked about that earlier, that when the copper 2 chloride dihydrate dissolved, the copper ions are in there floating around, and those are the ones that impart the blue color. And that gives you the hint. If there's any blue color left over, then that is in excess. Okay. Now, in this situation, though, in one of your chapters here, we were looking at molarity and concentration of solutes. So in this example, or in this question here, you're asked to define the concentration unit molarity, because there's molarity, molality, mole fraction, percent by mass. There's all these different concentration units. So molarity is moles per liter. Moles of what? Solute per liter of what? Solution. So when I take my 89 milliliters, like down here, and I do all this stuff to it, we're going to assume that 89 milliliters has stayed 89 milliliters, and that's my 89 milliliters of solution, which is 0.089 liters of solution. So we want to keep that in mind. Copper 2 chloride dihydrate initially was dissolved in water, given my 89 milliliters of water, and assuming that the volume does not change, because if it did, this would no longer be correct. Calculate the molarity of the copper 2 chloride dihydrate after dissolving. If I take my grams and I want to do molarity, and I know molarity is moles per liter, I would convert that grams to moles. Now you got to be careful, because this is at, no, we don't. We're okay here, because this is moles of what? Copper 2-chloride dihydrate. Okay, so that's the moles, and I know how many grams I put in there. I just convert the moles, and I divide it by my 0.089 liters. That'll give me the molarity of this guy that's in solution, including the waters. You know, we can look at them or we can ignore them, but they're still there. And we have to remember, and this is all about what's called solution chemistry, is when I take something and I dissolve it in water, and it's a solid, and I dissolve it in water, and if it's an ionic compound, it will create ions, right? And those ions would then have an aqueous label. And then it creates ions to the tune of how many ions were in the solution. Like I put 2 chlorides there, and this is now aqueous. And then the waters swam away. You could say, well, yeah, they swam away with the other waters, and they have a liquid label. So now if I had a 1.0 molar solution of this stuff, that's going to create 1.0 molar copper ions in solution, but it's going to create 2.0 molar chloride ions in solution. And if we wanted to play that game, it's going to create 2.0 molar of the released waters, which, if you want to play that game, this would be aqueous waters, which is kind of silly, but at the same time, it's not. It's just differentiating between the waters that came from there and the waters that were already in the water that it dissolved in. Anyway, so that's probably brought us to the next. We just did kind of letter B here. Copper 2 chloride dihydrate was initially dissolved in water. Given the volume, and assuming the volume doesn't change, calculate the molarity of the copper 2 chloride after dissolving. So I just pop it in there. The next one is calculate the molarity of the individual copper ions. That's what I was just talking about. If you do that first calculation in part B, which was this, say, it's going to directly correlate to that. That's because of the balancing. I know I get crazy with all the drawings of my lines, but if you look at our balancing here, 1 copper chloride dihydrate, 1, see them right here, will make 1 copper, 2 chlorides, and 2 waters. So when we do, like if I figure out my molarity here, like I did of the 1 molar, all I have to do is think about my stoichiometry, and then I'll know what everybody else is in solution based off of that. So that's what C and D was. And this Helmenstein is a really good site. I mean, these people do a lot of stuff on chemistry, and this was a nice example, this molar concentration of ions example problem, which is just kind of like what I did. All right, thinking like a chemist, trying to hurry up here. Chemistry is all about keeping track of everything in a solution before and after. Now that you know the mass of copper created and the grams of excess reactant remaining. See, so you would have had to calculate that already. So I have over there, you see, I have 2 pictures again. I keep on having those pictures because in the top example, the aluminum was in excess and there was 0 copper 2 ions left over, but there was aluminum left over. Okay, now in the bottom picture, you have this copper. You see copper 2 plus must have been in excess and now it's still in the solution. So given your scenario, depending on how much you got out of your quiz, to calculate the molarity of the chloride ions in solution after the reaction was completed. Now I have here but before filtration because in that video, he filtered it. And as the filtrate, if I want to do some quick artwork here, here was my funnel. And what he did was filter, and now you have this filtrate down here, and what he was isolating was the copper metal up in the filter paper. And then what went down here was probably some copper ions. If the copper was in excess, you'd have aluminum ions in there because remember, aluminum reacted into there. Then you'd have chloride ions in there, and you'd have so much swimming around down in there, but it can all be calculated because we know how much we put in. So anyway, for part E here, the idea was to calculate the molarity of the chloride ions in solution after the reaction was completed. Now, did we already talk about the chloride ions? We did back here. Calculate the molarity of the chloride ions before reaction. Now you might question, was chloride even really involved in the creation of the copper, or was it the aluminum? So that might give you a little bit of a hint, because if chloride turns out to be a spectator ion, the molarity before reaction and the molarity after reaction should be the same. So when you do your calculations, make sure that is true. Do not report different amounts of chloride, because that's kind of impossible. It was not changed. The chloride ion was not changed. Okay, so now this one gets a little bit more sticky though. This part F, calculate the molarity of the copper 2 ions in solution after the reaction was completed. So we are going to assume that, I mean, we don't have to assume, we know that some of the water, not the water, I'm drawing water, that's why I said the word water. Some of this copper that turns out to be in solution is going to react with the aluminum to create aluminum chloride and copper metal. So some of the copper metal was created from the copper ions in solution. So you will have a molarity of the copper ions in solution before reaction. That was calculated like we did on the previous slide. And then you'll have a molarity after. That's because so much, and you have to figure this out, so much is going to be eaten up of that copper to create this stuff over here. So if it turns out that this guy is in excess, you would have to subtract the number of moles that were eaten up or reacted with by the number of moles of aluminum. So let's say for giggles that 0.010 moles of aluminum went into the flask and ate up zero. So that means, and now we have to think about balancing here. We have to think about balancing, because here's this water. And then if we balance this, if you remember, there was a 2 here, and there was a 2 there, and then there was a 3 here, and there was a 3 there, and then this turned out to be 6. We have to think about balancing, because if we don't, we're going to get lost. So if we say I had 0.010 moles of aluminum, that's how much I put in there. Well, how many moles of copper to chloride dihydrate would that react with? Well, that's where our stoichiometry comes in. And we say, okay, I have a mole ratio of aluminum to copper 2 chloride, and it's 2 to 3. So that means I would take this 0.010 moles of aluminum, and I would convert it from moles of aluminum to moles of CuCl2.2H2O, and use the mole ratio for moles of aluminum to moles of copper chloride dihydrate, and that's a 2 to 3. So if I get out my calculator, two divided by 3 is 0.666. So if I say on 0.01 times 2 equals divided by 3 equals, that's 0.00. 0.0066 repeating. Now that is the number of moles of what? That's the number of moles of aluminum. No, boy, I messed that up, didn't I? Let me go back. Totally messed that up. It's always nice to make mistakes, because then you can figure it out again. So let me change that. And you know how I caught that is, and this is where dimensional analysis happens, because we just get into overdrive, you know, and we're just we're on cruise control. So I was on cruise control, but I should have been on cruise control to put aluminum down here and copper chloride dihydrate up there. So anyway, it happens. So now I got to change my numbers, because now it's 3 to 2. So now I get out my calculator again, and I say 0.01 times 3 equals divided by 2 equals 0.015. 0.015 moles of CuCl2.2H2O are required. Okay, that's what I just calculated there. are required to react completely with my 0.010 moles of aluminum. Well, let us say that we had that the copper 2 chloride dihydrate is in excess. And let's say that we started out with 0.017 moles. Now, how do I know that? I mean, I got grams from the quiz, and I turned grams to moles, and I put it right there. And then I'm saying, well, I must react out 0.015 moles. How much is left over? And I just do the math. 0.002 moles, that's now left over, and it's in excess. So what that means is what I was trying to do in letter F was calculate the molarity of the copper 2 ions after the reaction was completed. So let's see what we remember from before. If I take this 0.002 moles of CuCl2.2H2O, and I want to say, I'm trying to figure out the molarity of the copper ions only. Well, I can use a little dimensional analysis to say for every 1 mole of CuCl2.2H2O, there is 1 mole of copper ions present. Now, all I was looking at was the number 1 right there. I don't know if you saw that. The number 1 right there, to put the 1 right there. And now I know what the molarity, number of moles, of copper 2 plus is. It's 0.0020 moles of Cu2 plus. But that's not what it's asking for. It's asking for the molarity. Well, molarity is moles divided by liters of solution, which I know was 0.089 liters. And that would give me a molarity after reaction. And of course, it must be much less than what I started out with because it did react with. But if my solution was blue, like up here, that means it was in excess. Okay, so I'm going to get rid of all this stuff. And now the question was, this next one here is to continue this analysis. Actually, I'm not going to get rid of it yet. To continue this analysis, what about the water molecules that were locked in the solid hydrate? Remember how they were locked? Sorry about that. Remember how they were locked in over there. Here they are. They were locked in over there, but then they were set free over here. Now, the number of those water molecules that were set free can be calculated. I know you're thinking, wow, that sounds so exciting. It can be calculated because I know how many moles of total, I should have circled the 3, how many moles of total copper chloride dihydrate I put in. And then I know the mole ratio, 3 to 6 or 6 to 3, however you're doing it. And then you can figure out the number of moles of water that were released. And then you can take that moles of water to molecules of water using Avogadro's. So anyway, that's just having fun with Avogadro's. All right, onward. Part 6, oxidation numbers. So what was part 5? Part 5 was just molarity. It's thinking like a chemist, being able to look at your cup of coffee and say, I know that's coffee, but I can see those sugar molecules swimming around in there with the waters. Or the coffee molecules. And this one, part 6, is oxidation numbers. And when we study these reactions, what we're really dissecting is what's happening to those individuals when they're in there. So many chemical reactions are labeled redox. What is redox? Redox, by definition, is a reaction in which electrons are exchanged from one atom that has electrons to give to another atom that wants to take them. So of course, this is like a working together thing. One atom wants to give, one atom wants to take. If you don't have that, or one atom wants to give, or one atom wants to give, but the other one doesn't take, that's called no reaction. And that happens a lot of times. If you have one that wants to take, but the other one doesn't want to give, again, no reaction. But if you have a situation where there is a give and take because of what was called the activity series, Yes, you guys just did the lab. There's a lab in this class that is called chemical reactions, and you have the aluminum metal and you put the different things on there. And sometimes you see a reaction if aluminum is more active or whatever than what was in the solution. That's what you're seeing here. So explain what a redox reaction is. We just said that. For the reaction that we're dissecting in this project, determine if it's redox. So it's a good idea to write that reaction again. I mean, you're doing this as a typed document, so you could copy and paste this over and over throughout your through your document. Uh-oh, made a mistake. We're reacting this guy with aluminum. So you just keep on doing this over and over again. Now, it gets kind of sticky because, you know, this was a solid, but I had to dissolve it in the water. And then I had to add the aluminum, which was a solid. And if you recall, a couple slides ago, I wrote a 0 with the aluminum and the copper. Those are redox numbers. Oxidation numbers are a representation of the number of electrons lost or gained by an atom. So when an atom, like copper, goes to copper 2+, it must have lost electrons. And I write them over there. See how this 0 is now +2. And I like to show some math here that 2 times -1 is -2. And I add that to a +2. And guess what I get? I get 0. These redox reactions must balance in that fashion. So that kind of helps you sometimes, you know, when you're trying to figure stuff out. You can just start plugging in numbers and making sure that everybody's behaving. Okay, and then I'm going to continue my reaction right up here. And this is going to make aluminum chloride. And that's aqueous. Plus 6 waters, and those are liquids, or aqueous if we're saying, oh, they're the waters from the hydrate, but generally waters are liquid. I mean, that's what they are. And here we have solid, and there we have, okay. All right, this is not balanced. I would have to put a 3 there, and a 3 here, and a 2 here, and a 2 here. Okay, for the reaction we are dissecting, determine if it's redox. Well, how to determine if something is redox is to assign oxidation numbers. So the oxidation number on copper in copper 2 chloride dihydrate is +2, just like I have written here. The oxidation number on aluminum is +3. How do I know that? Because there's 3 chlorides with it. And so if you kind of dissect that out and you say I have AlCl3, well, what makes AlCl3? Aluminum 3+ and 3 chlorides, which are each -1. So those are redox numbers. Now you can also assign oxidation numbers to covalent compounds, like we do with water over here. Look up at water in the upper right. Hydrogen, by its most common oxidation number, is +1. The most common oxidation number of oxygen is -2. I have to look at it though and see if that's true for this case. For these oxidation numbers, when you're trying to figure them out, you kind of have to know one to figure out the other. So many times in these ionic compounds, the one that is negative is written second. Even in these covalent compounds, look up there. So that kind of gives you the idea of, oh, it must be negative in this case. So that's just a little heads up on that. So when a redox reaction occurs, there's an oxidizing agent and there's a reducing agent. The agent, when they say that agent, that means reactant. So there's a couple reactants here. There's copper 2+, there's chloride floating around, there's water floating around, there's aluminum metal that was put in there, and then it changed. Copper solid showed up, aluminum is now swimming around as an ion, chloride is now swimming around as an ion, and water is just swimming around with the rest of the waters. So what you're looking for is who's changed. Has water changed? No, water was the water on the left and water was water on the right. So if you go through and look at this, you can assign numbers, +1, -2. +1, -2 did not change. That means hydrogen was not altered here. Whereas copper, +2 to 0, that was altered. And when you notice the number going down like this from 2 to 0, that's a reduction. And sure enough, that means copper 2+ was reduced and then was reduced by how many? By 2. And who was it reduced by? It was reduced by the other thing that changed, which is aluminum. So aluminum's oxidation number went up. It went from, there's my arrows. It went from 0 to +3. That is an oxidation. When you have a number rise like that, its oxidation number goes up. That's an oxidation. If the oxidation number goes down, that's a reduction. And sometimes you'll see some little ways to remember this. I remember the oil rig one, oxidation is loss of electrons and reduction is gain of electrons. So that's how I remember that one, oil rig. So anyway, that's talking about the oxidizing agent and the reducing agent. So the idea is to look at it and say, who's being reduced and who's being oxidized. So on this little GIF I have down here, I just put this on here because I love GIFs. If they're reaction GIFs, we can look at them. Sure enough, and what's so cute about this GIF, if you notice the hydrogen is trying to float away, and that's because it is a gas. And as it's being created, it's leaving the solution. And if we were to play around and assign some oxidation numbers here, zinc is 0 because it's a metal and it's elemental. Hydrogen is 0, it's elemental. If we break up hydrochloric acid, we would see +1. We see chlorine here, it would be -1. If we see zinc, +2. We see chlorine, -1. So if you look at this, it might, and I asked you which one is oxidized and which one's reduced. Zinc's number went up, so that's an oxidation. Hydrogen's number went down, so that's a reduction. The spectator ion in this case is chloride. Chloride is a spectator a lot of times. Anyway, I think that's about it for this slide. So let's keep on going through. We're almost finished here. Part 7 is aqueous chemistry. Still thinking about what's going on in the solution. That's why I still have this GIF down here, because we will see some bubbles. We'll talk about that in our course as well. Now, this is talking about ionic equations. And I can give you a quick example of an ionic equation using this one, so you can apply it to your project. Zinc, in this example, zinc plus hydrochloric acid. And if I were to put phase labels on this, I would have a solid and I would have aqueous. When it's aqueous, that means something to us. That means it's dissolved in water. So as chemists, we look at this and I say, do I want to drink a cup of coffee that has solid material in it? Well, it depends if you're from Turkey, right? Because then you're drinking that stuff with all the sludge in it, which is fine. That's okay too. But most of the time, you really want it to all be aqueous, right? So it goes down a little bit easier. So what I created here was zinc chloride plus H2. Now this guy's a gas. This guy is aqueous. Zinc chloride is aqueous. What is this? This is called a molecular equation, and the molecular equation is showing them as if they were together. Now, technically, they're not together. That's because when things are aqueous, that means they've dissolved in water. And by definition, dissolving means the solvent comes through and rips the solutes kind of apart from each other. If it's ions, those ions are going to be separated. If it's molecules, the molecules will just swim around. Okay, so to write the complete ionic equation, what we do is if it's an element and it's a solid or a gas or a liquid, it's going to remain that. Zinc metal does not dissolve in water. But if it's aqueous, that means these ions are now separate from each other. But how many of them? I mean, if we look at our balanced equation, there's 2 of these and then there's 2 of those. All right, let's do the other one. If I look at this, it's aqueous, so that means it's soluble in water. And now I'm writing the ions up there, zinc. And it is, if I was going to be tedious about this, I would label every single one as aqueous, because ions, you have to kind of say what they're dissolved in, and that's what that is. Now, again, this chloride, when this zinc chloride dissolves, there's 2 of those there. And and the hydrogen is a gas, so it stays. H2 gas. Okay, so now the complete ionic equation is showing everything. The net ionic equation is showing how the spectators cancel. So spectators, just like in mathematics, on opposite sides of an equation are things that are in the same form. So I find them like here. If I were to subtract 2 Cl's from both sides of this equation, it's like math. It's like you're not doing anything to it. So, but those things are definitely canceling out. But the other ones, you don't see them in the same form on either side. So what I just did there was cancel the spectators. And what that leaves is what's called the net ionic equation, which is that. Zinc solid plus 2H plus to make zinc 2 plus and hydrogen gas. And it's balanced. That is called the net ionic equation. Now there's this half reaction thing, and I did have some half reactions on the previous slide. Half reactions are what show kind of the involvement of the electrons. Now, zinc in this case is being oxidized. So I'm showing the electrons being lost from the zinc metal on the reactant side. Now, if I was going to do that with the hydrogen, I would do the same thing, but it's going to be flipped. I'm going to do that over here. You have H plus, and there were two of them on a reactant side, and then I made H2 gas, and it had 0. So it went from +1 to 0, and +1 to 0 is a reduction, and that is a gain of electrons. Now that's a +1. +1 to 0 is a difference of 1, but there are 2 of them. So I need to have 2 electrons come in, add to the hydrogen, and make H2. And now this H2 is stuck together. As when it leaves as a gas, they're actually stuck together. Oop, they're stuck together, and off they bubble away. So now when I have these 2 half reactions, where did those 2 electrons come from? Well, it must have come from the zinc. The zinc gave them, the H plus took them, and then your overall reaction does not show the electrons, but it shows the interchange, the result. So those are half reactions, and hopefully that will help you in your project. Finally, side reactions. I think we've covered enough in here that you guys could probably look at this now and go, oh, now I see kind of what's happening. This little analysis down here should help you, because zinc is a heck of a lot like aluminum. And this is talking about in its reaction with hydrochloric acid. So this is talking about doing the same type of analysis that we just did with zinc with aluminum. So you have aluminum plus hydrochloric acid to make hydrogen gas and aluminum chloride. And then it just kind of goes through the motions, looking at that redox nature, looking at the electrons, looking at spectator ions, same type of thing. And then finally, to report your results, like a chemist or like any scientist, or it doesn't, any scientist, when you report your results, whether or not you're in culinary school or whether you're in chemistry school, you're just reporting it in a way that somebody could read it and understand it and maybe even reproduce it. So in 2 to 4 paragraphs, I asked you to write a summary of what the experiment did and what you observed. I mean, like you watched that video, say in this reaction, copper 2 chloride dihydrate was dissolved in water. Aluminum metal was added to that. A reaction occurred in which you saw this was observed. And then you just go through and talk about that. I asked, and then kind of like, just so everybody could be on the same page. And you could even include pictures like this. Those are kind of nice. So when he was doing that experiment on the video, you could stop the video and take little screenshots, and put it in your report. Identify the type of reaction for the copper 2 chloride dihydrate and aluminum reaction, as well as the aluminum and hydrochloric. So if you remember, there's different types of reactions. There's metal displacement, there's double displacement, there's redox. Of course, they're all redox. So, you want to probably come up with something else there as a descriptor for those types. Describe the results and calculations that led to the determination of the limiting and excess reactants. So if I asked you, well, how'd you do that? Well, you might say, so many grams of copper 2 chloride dihydrate was found from the quiz, and so was the aluminum. I converted both of these to moles, compared them, saw who was the limiting and excess, and state those results. Might want to even pop in that table and show that. To recap in words how you calculated, because the more you recap something, the more you learn it, and the more you learn how to think like mathematically. Calculated values should match experimental evidence. What does that mean? If you tell me that the aluminum was in excess, but the solution is blue, that's a problem. Because then if the aluminum was in excess, like I have over here in the upper right, you would not see any blue. If the copper 2 chloride was in excess, you would see blue, but you wouldn't see any aluminum. So that's where you have to be on the same page with yourself, when you're reporting these reactions and reporting your results. Finally, identify the percent yield. This is like it's like a final result. The percent yield was found to be for this reaction, given who was excess and who was limiting, and then explain what factors could affect your percent yield. And the side reactions, when those bubbles were occurring, it wasn't the copper. It was the aluminum reacting with HCl in that bucket. That this is a very complex reaction, actually, but then we talk about it. So anyway, that's why I put that in there for the side reactions, Because you would think if you got a side reaction going on at the same time as your main reaction is probably not going to be as successful, and you're going to end up with less of it because this guy's over here stealing your reactant, and your reactant happened to be aluminum metal that was doing the process. So anyway, hopefully that helps you. I'm going to stop here. And if you have any questions, go ahead and put them into the discussion board, and I'll post this on an episode. Thanks again. Nice meeting everybody. And hopefully this will help you on your project.